I will begin with a word of prayer. Dear Father, we thank you for this day again, Lord. Thank you for these students. Just ask you to help us use this time wisely, Lord, for your glory. In your name I pray, Lord Jesus. Amen. Okay, so first things first, by request, this is example 4.5.24. And here I give us a vector field A, which when we feed it x, y, z, it gives us y squared, x, and sine z. All right, and then I look at a parameterization of a graph, r of u v, and that's given to be u, comma v, comma f of u v. All right? And so the question is to calculate partial u and partial v of the composite of A and R. So, by the way, of course, all of these chain rules it's all about differentiating, composite functions. So let's see here. So first of all, so let's see, partial u of A composed with R, all right, of course at uv, all right. How's that work? So what that is let's see here. How can I write it this way? Let's see here. What's the best way to note that? Okay, very good. So that's partial u of y squared, x, and sine z, where what? Where x is equal to u, where y is equal to v, and where z is equal to what? F of uv, right? So that, guys, by definition, is partial u of y squared, partial u of x, partial u of sine z. So when we partial differentiate a vector of functions, we partial differentiate one component at a time. That's the rule for the calculus, okay? Just like when we differentiate a path, none of you even flinched when I said the derivative of a path is the path, we differentiate one component at a time, right? None of you complained. You're like, what? Why did you just differentiate the first component and leave the other two alone? No one says that. Everyone's like, oh, okay, that's how we differentiate. In the same way, if we're partial differentiating a vector of functions, we just differentiate one component at a time. But then each one of these is separately a chain rule problem, right? So what's the chain rule look like here? It's not especially exciting. This one is 2y partial u. This one is just partial x partial u. This guy, we got cosine of z partial u, right? What is partial x partial u? What is partial y partial u? Partial x partial u is what? Is 1.
Partial y partial u is 0.
Right. And partial z partial u is what?
Right.
Yeah, partial z partial u is actually partial f partial u in this context here.
Yeah,
You're fine. So where are we? This was 0. Partial x partial u is 1. And then we've got cosine of z. And then partial f partial u. Now in the notes, I also, well, I have this, I have expanded on this a little bit. I replaced the z with what it is. You know, what is z? It's f of u comma v. So I've explicitly, removed, I've removed reference to the intermediate variables and just left it in terms of the independent variable and the f, the given f here. So that's that. Now, the second half of this example in the notes is currently incorrect. So I'll go through that. Second half of the example, partial v of a composed with r. So that's going to be partial v of the first component of a, which was y squared, partial v of the second component of v, which was x, as it happens, a. Third component of a was sine z. So essentially the same calculation. We have 2y partial v partial y. Partial v partial. 2y partial v. Over here, we've got partial x partial v. And finally, we got ourselves a cosine z partial v. But remember, x, y, and z here are given to be u, v, and f of u, v, respectively. So like partial x partial v is 0. But this time, we have 2y, right? 0. Partial y partial v is what? It's just 1, right? And so that gives us a cosine of z. And this, of course, is partial f partial v, right? But if I put that in terms of the u and the v's, that's nothing more than 2v, 0 cosine of f of uv partial f partial v. So that was the... See, but my notes right now have an error because instead of putting 2v in the first component, I mistakenly have a 1 there right now, which of course is a typo or an error, depending on how you want to look at it. But I have that as 1 in the notes, which is wrong. Okay? Yep.
For the notation when you set up the partial v of the r, that you wrote that slightly different for the other one. Are you saying
you can always write more dependence down and how much you write. How much do you want to write? I don't know. At some point, we stop writing things, and it's just understood, because otherwise, to be correct is to write very much. And I found that if I ask you guys to write too much, you just stop at some point. You're just no, you can't make me. And I'm not sure where that line in the sand is, but I'm just trying to stay away from it. I don't want to get there with you guys.
I should know if you were saying something different.
No, I wasn't. There was no secret. This could be abbreviated, right, as partial u of a composed with r, with the understanding that we're differentiating that function of uv. Yeah. So that was one example. The other thing I was supposed to do last time, and I neglected, was how to changing coordinates for partial differential operators. All right. So here's how you do it. So suppose here's a typical problem task. Write partial x and partial y in terms of partial r and partial theta. All right? How would you trade a partial differentiation with respect to x and y for a corresponding partial differentiation with respect to r and theta. Now when
Did you put it in cylindrical coordinates?
right, but how do we actually do that? Like, how are these specifically connected? And I mean, right, so correspondingly, we're going to take the function we're differentiating, right? And maybe the function's originally written in terms of xy notation. We'd swap that xy notation out for like r theta notation, right? So like instead of differentiating, for example, I might have the function x squared plus y squared. In the polar presentation, that function would just be r squared function, right? So like this discussion is paired with a rewriting of the functions we're differentiating, although I'm not even going to write the function. I'm going to show you a method for changing the partial differential operators without even writing the function we're differentiating. Okay, so like this is how you do it. It's pretty simple. I mean, as a rule, it works out like this. So partial x, we can trade for partial r, partial x, partial r, plus partial theta, partial x, partial theta. That is the chain rule as it applies to partial differentiation. Right. And likewise, we can calculate partial y in terms of polar derivatives as partial y, partial r, plus partial theta, partial y, partial theta. So then, of course, the question is, how do you actually calculate? How do we actually calculate such partial derivatives, right? So in order to calculate these partial derivatives directly, I need to write r and theta as functions of x and y. Now we've done this before, right? Recall, r is the square root of x squared plus y squared, and theta is equal to inverse tangent of y over x for x. And I'm just going to say, I'm going to do the calculation where x is greater than 0. In fact, almost the same calculation would go through when x is less than 0 by just adding pi. The derivatives are all the same. But I'm just going to suppose x is greater than 0 to keep things on the level here, all right? When x is greater than 0, inverse tangent actually gives me the honest to goodness angle for y over x, right? For x positive. Okay, so what is partial r? Remember how this goes? Partial r, partial x is what? It works out to x over r. Partial r, partial y is y over r. I would remind you of Nathaniel's suffering in the daily quiz of about 10 days ago, right? It was over there. You should be able to work these out, right? It's 1 over 2 times the square root of x squared plus y squared times chain rule gives me a 2x upstairs. The 2's cancel. That leaves me x over the square root of x squared plus y squared, which is x over r. Anyway, you can work those out. How about partial r, how about partial theta, partial x, though? We also did these the other day, right? I think when we were calculating theta hat, we worked this out, and I've forgotten what we got. I think we got, well, let me just go through it again. So this is what, 1 over 1 plus y squared over x squared, right? Times the partial derivative, which is what, minus y over x squared, right? Then multiply through that x squared. What does we get? What does it give us? Minus y over x squared plus y squared, right? So thus, partial theta, partial x is equal to minus y over r squared, right? And likewise, we can calculate that partial theta, partial y is equal to what? It's x over r squared, but yeah. This, when you do the partial differentiation with respect to y, the y appears in the numerator, so the chain rule just pops out a 1 over x which then you multiply by x over x to create the x squared in the denominator to clear out the y squared over x squared, leaving us with r squared downstairs and an x upstairs, but no sign because y and x appear differently here. Similar, but not the same. Seems wrong to say that. They're similar, but not the same. I mean, can we say that? Oh, okay. I see some nodding. I mean, they're like each other, but they're not. Okay, anyway. Excuse me. Getting to the point, what have we found? So, in summary, we just worked out that partial x is equal to, what is it equal to? Partial x is x over r partial r plus y over r partial theta, right? And partial y is equal to, what is it, minus y, if I could do math. Oh, no, I'm so sorry, guys. I am, what's the organization here? I mean, I actually need to, like, connect the thoughts, right? I mean, do both of the, how are these calculations, they go back to that, right? So, what I'm trying to say here, if I could find my words, I'll eventually find my words. Give me a second here. So, going from my chain rule right here, right, using this and what else? This one, right? Those two together give me x over r, right, minus y over r squared partial theta, right? And the other ones, the partial y derivative, I need this guy and that guy, right? And that gives me what? That gives me y over r, partial r, right? Plus x over r squared, partial theta. Now, the expressions I've written down, they're not quite the best because they're a mixture of Cartesian and polar things, right? Like, we really want to own it. We really want to own this. We want to make it completely polar on the right-hand side. Like, so I need to convert the x over r and the y over r squared into polar coordinate expressions. How can I do that? How can I make this better? What's x over r? I'll help you guys out. X equals to r cosine theta. Y equals to r sine theta, right? You know this. X over r is? So we got ourselves a cosine theta, partial r, right? And how about this one? Yeah, 1 over r sine theta, right? Partial theta. And how about this one? This one is, what we got? Sine theta, partial what? R. And then plus 1 over r cosine theta, partial theta. So there you go. These are how to convert the y derivative and the x derivative over to r theta derivatives. Just like that, or like this. How would you go the other way? What if I wanted to convert r theta derivatives to xy derivatives? How would that calculation look? So what would the chain rule look like in that direction? In that direction, I would do something like this. Partial r is what? It is partial partial x, partial r, partial x, plus partial y, partial r, partial y. And likewise, partial theta would be, partial x, partial theta, partial x, plus partial y, partial theta, partial y. Now these happen to be way easier, way easier to calculate. Like what's partial x, partial r? All you guys got to do is you got to go back, or just look in your mind. Hopefully it's in your mind. Wherever you got to look, but you should know this. X equals to r cosine theta, y equals to r sine theta. That's, how we relate x and y to r and theta. So what's partial x, partial r? I heard a cosine theta, right? Cosine theta, partial x. And what's partial y, partial r? Sine theta. Partial y, right? And how about these? You got yourself a minus r sine theta, partial x, plus r cosine theta, partial y. Just differentiating those expressions over there. In fact, another way to do these calculations, if you're brave, is to first do what I did in blue, right? And what you could do is you could look at it as like two equations and two unknowns. You could solve these equations for partial x and partial y. And if you did that, treating partial x, partial y as variables, you would actually derive the equations that we derived over here, these boxed equations. You could do algebra on the blue equations to get to these boxed equations over here if you were so inclined. All right? Let me just pause for a second here to show you how this works on a specific example. Otherwise, this is just kind of hocus pocus, symbol pushing. What if we look at, say, f of x comma y equal to, let me suggest, I don't know, how about like x over the square root of x squared plus y squared, right? Plus x squared plus y squared. So we could calculate partial f, partial x. What would that look like? You could do it, right? What would it look like? Oh, it's unpleasant, isn't it? So we have to differentiate this thing, which is what? Yeah. Let's see here. I'm going to do it as a product rule. So it's like 1 over the square root of x squared plus y squared, right? And then minus x times 1/2 x squared plus y squared to the, minus 3/2 times 2x again, right? Doing the product rule, because x times 1 over the square root of x squared plus y squared is a product of the functions of x. So I do the derivative of the first times the second, plus the second times the derivative of the first, or vice versa. Anyway, product rule, these two terms, then that gives me plus 2x.
Wouldn't that just be x for the second part of the product rule?
Yeah. Oh, fair enough. So what we got is partial f, partial x is equal to, you got 1 over square root of x squared plus y squared. And like you just told me, there's a minus, right? So minus x squared divided by the square root of x squared plus y squared cubed, I suppose. We could write it that way, plus 2x. There you go. That's how we do the differentiation directly. What if we tried to do this differentiation in polar coordinates? How would it look different? If for some reason you wanted to calculate partial f, partial x in terms of polar coordinates, what would that look like? So really, I'm asking the question is, what is, partial f, partial x in polars? Let's see here. So What did we just figure out? We figured out partial f partial, figured out partial x was what? It was equal to cosine theta, right? Partial r minus 1 over r sine theta partial theta, right? And then this f, what is f? If we convert f to polar coordinates, what is it? Yeah, the first term is x over r, right? So the first term in f is nothing more than cosine theta in disguise, right? So it's got a cosine theta, and then what's this? R squared, right? So when you calculate this partial derivative, this on this is 0, and this on that is 0, all right? Only the partial derivative on that term matters. So what we get is we get a 2r cosine theta from the first piece, and then we get a minus 1 over r sine squared theta on the second piece. Curious. Well, and so what's going on here? Did I miss something? I don't think so. It's 1 over r. Yeah. All right, so does this make sense? Are these the same answer, just in different coordinates? I mean, that's what I'm claiming, is that this is just a different way of calculating the same beast, whether we pick x, y coordinates or r theta coordinates. Well, this right here, you might recognize, this is 2x, right? That's 2x. So that's this piece. All right? What's 1 over r sine, what's sine squared theta? See, this right here is minus 1 over the square root of x squared plus y squared. And sine squared theta is y squared over x squared plus y squared, right? That's what that term is. So I think you got to use your imagination a little bit to see. So somehow we got to combine these two things. Yeah.
Could we use the relation 1 minus cosine theta squared equals
That's
sine squared?
that's probably a good idea. So you say it's going to save me trouble.
Yeah.
I think you're right, because then that trades my y squared for a 1 minus what? X squared here, right? I like that. I think that's helpful, because then you can see, right? This gives us a 3/2 power, so that's this term, right? And then over here, what's going on? Actually, that's a plus x squared. That's no bueno. Huh. If you see someplace I've made a mistake and I'm missing it, let me know.
I think I see it. When you're differentiating at on the right side at the top, the derivative of cosine is negative sine, not sine. So that it would
Ah,
be positive.
thank you. That's helpful. That's helpful. Indeed, this should be a plus. So that makes that, at least these terms match up. The x squared over x squared plus y squared to 3/2 power makes sense. What it probably, well, it might be helpful to just put this into one term, right? How to make a common denominator, how would we do that? Yeah? So that gives me y squared over x squared plus y squared to the 3 halves. So, sorry, but I'm going to go back on your suggestion and go back to my y squared, because then, yay, same, yeah. I think you should believe me when I tell you that doing this differentiation in polar coordinates is nicer, right? Like if you look at this function from this perspective of polar coordinates, it's actually kind of a nicer calculation. All right. Anyway, whether or not it's nice, we do want to be able to restate formulas in engineering and physics and other things in terms of non-Cartesian coordinate systems. And this is the math we need to understand to do that. For example, Laplace's equation. What's Laplace's equation? Laplace's equation states, partial squared, let's say partial squared u, partial x squared, plus partial squared u, partial y squared equals to 0, right? You can this is Laplace's equation, all right? So the second partial derivative with respect to x plus the second partial derivative with respect to y of a given function, if that's equal to 0, if it solves that, then this function is a solution to Laplace's equation. In fact, such functions are said to be harmonic. Study of harmonic functions is an interesting and deep topic. What does this look like in polar coordinates? See, to figure that out, what would you have to do? This is really partial x, partial x, right, of u, plus partial y, partial y of u. So if I want to convert this to polar coordinates, all I got to do is take these handy-dandy boxed formulas right here and put them in here and face the music. I mean, there's a lot going on here. This is I'll just pick on the first term. It'd be cosine theta partial r minus 1 over r sine theta partial theta. That cosine theta partial r of u minus 1 over r sine theta partial theta of u. So I'm just showing you how I would calculate this piece right here, okay? So you convert partial x to the r theta derivatives, and then you convert partial x to the r theta derivatives again, but when you do that, what do you end up, the trouble with that is what? See this u? U could be a function of both r and theta in principle. So you've got a product of the functions of theta here. You got to do product rule. When this theta, partial theta hits that, you got to do a product rule. And over here, you also have a product rule, because this partial r hits 1 over r, and this function over here, which are again functions of r. So you got 2 product rules, you got to do both of them. I'm not going to write it out, it's a mess, right? After a while, though, you'll come to the result, which I do not have memorized. Maybe I have written down in a place I can find it right quick. Give me a second here. I mean, I remember this much. The formula for the Laplace's equation in polar coordinates. Come on. Oh, stink. I have assigned this as homework question before. Did I assign it to you guys? I think I didn't, because it's kind of a lot of pain and suffering to work that out. Oh, I did? I did. It is problem 118 at the back. If I did, I'm sorry to tell you, the solution's also posted. Because it's problem 118. Although this may be one of those, every so often there's a problem in the solutions I don't have a complete solution for. But problem 18 tells you how this works out. 118, rather. So, no. All right, so problem 118, it ends up being this. Partials, and I'll write it in terms of u rather than big phi, since I used a little u for the function. Partial squared u partial r squared. And then here's the funky thing. 1 over r partial u partial r plus 1 over r squared partial squared u partial theta squared equals to 0. This is what Laplace's equation looks like in polar coordinates, which is kind of surprising, right? Laplace's equation in Cartesian coordinates just involves second derivatives, but Laplace's equation in polar coordinates picks up a first derivative term. So you're like, well, what would this matter? Well, this would matter if you're trying to, for example, find lines of equal voltage on something like a disk. A disk often is naturally modeled by polar coordinates, and so Laplace's equation is most naturally captured in this formula for something that's got like a circle or a disk. If you're trying to, find the voltage function on a disk, this is the sort of thing that might be relevant. There's a theorem. If you got like a disk like this, right? And if you specify the voltage, let's say u of r kind of theta on edge, all right? If you specify, the voltage on the edge, all right, then you're going to be able to solve Laplace's equation inside there to match that voltage function in a unique way. Anyway, I digress. Okay, so enough about that. I hope that's enough that you get a sense of how to change partial derivatives from one coordinate system to another. Do you guys understand the pattern? I mean, it's kind of a drag, right? But it's relatively straightforward what you do. It's kind of this conservation of partials thing again, right? Like there's a partial, I've lost it, but here's a, you can't see it in this notation. I've erased the relevant formulas. Yar. Oh, here. You notice that there's a partial r here, but there's also one where here and here. But to be fair, r is a function of both x and y, so the chain rule has to peel out a partial x and a partial y. Right? If r was somehow a function of x, y, and z, there would also be like a partial x, partial z term. So did I assign 118 in the?
Your sign one was spherical.
No, it's not spherical coordinates. You gave us the definitions of a unique coordinate system in U and V.
Oh, yeah. Oh, man, I even told you the chain rule. Oh, I'm getting to be too nice in my old age. Let's see here. So yeah, that what problem was that, Nathaniel? Which number?
58.
Yeah, problem 58 is very much related to what I just did. Okay, so the other major topic that we have not really touched much on yet, and that I should start at the beginning and try to talk carefully through in the remaining time today, is differentiation with respect to side condition. And so let me just start here. This is my section 4.7. Partial differentiation with respect to side conditions. Now, this terminology with respect to side conditions, I got it out of, I think, Thomas's calculus. Not everyone says that. Let me say, here's really more what this is about. The question is how to take partial derivatives in less than clear contexts. You're like, oh, that sounds unfun. Well, we're going to make it fun. It's not going to be that bad. Let me show you. So, example 4.77, I should have stuck with it last time. It has everything we need. So W, suppose we have W equals to x, y, z. All right? Okay? So one of the things I want to teach you is that we can calculate the differential of this, right? What's dW? We can also calculate, we can solve this for z, right? Z is equal to what? Z is equal to W over xy. We can also calculate that. And we could calculate dz. What's dW, though? You guys still haven't told me that. I'll get you started. Yz dx. What comes next? Xz dy. See, have courage. You knew this already. Plus what? Xy dz. What's dz? Okay. Then what? Minus W over x squared y dx, right? Minus W over x squared y, oh, excuse me, xy squared rather, right? dy. So what I'm going to attempt to communicate to you in the next 10 or so minutes is what I loosely call the method of differentials, all right? The method of differentials is an informal method of calculation which helps us figure out partial derivatives. By just taking total differentials, which you can do without thinking, we just did, take total differentials, and then interpret. So here's the interpretation part. This coefficient right here, all right, this tells me whatever this coefficient is, that is partial W, partial X, because there's a W over here. This one right here is partial W, partial Y. This right here, that is partial W, partial Z. Of course, you're like, I know that. That's how we just calculated it. What's your point, right? I mean, how did we just come up with the total differential? We did those things, did we not? All right. Down here, what do we have? This is partial Z, partial W. This guy, partial X, oh, I'm sorry, I can't do math. Partial Z, partial X. And this one, with the minus included, that's partial Z, partial Y. All right, so I guess my next question is, yeah, you guys have a question? Oh, okay, so I guess my next question for you would be, up here in this world, what is partial? If you look up here, right, and I asked you the question, what is partial Z, partial X, what would you tell me? Ignoring this. What's partial Z, partial X up here?
Partial y, W, partial
I mean, how did we do these differentiations? We assumed that x was independent from z, right? So our default assumption in writing this down is actually that partial z partial x is 0, right? I didn't even write it, but it was assumed in this calculation, right? But then, down here, partial z partial x is minus w over x squared y. By the way, that's not 0. Well, this is going to be a real pain for me to grade, right? Because who knows how many answers there are. This is very troubling, isn't it? So what's the solution to this seeming contradiction, this paradox? How do we resolve it? Why are these things actually not at odds? The reason is very simple, actually. The reason is above and below the line, which I should have given a different color, for example, orange. Above the orange, the sad orange line that's barely visible. Enough of this. I almost still didn't get Ian. I'm trying. Eventually I'll hit him. I got to aim for the hat. So above the sad colored line, we're treating x, y, and z as independent variables, right? Above that line, w is a dependent variable in terms of x, y, z, right? That's the perspective of the mathematics. That's what we're doing. We're treating w you could write it this way. W is equal to w of x, y, z. Down here, what's the perspective? Down here, we're thinking z is a function of w, x, and y. So up here, x, y, z, independent, right? Down here, w, x, and y are independent. So this hopefully draws your attention to a core concept of partial differentiation, which is that partial differentiation does not happen in a vacuum. If you just talk about partial differentiation with respect to x, that does not make sense. You must, to properly understand what partial differentiation with respect to x means, you actually have to say what other variables are out there and which other variables you're taking as independent with respect to x. If you don't state the set of variables which you're taking as independent, the partial differentiation is not well defined. Different choices of independent variables give different partial derivatives of the same variable with respect to another. That's the point of this example. 0, not the same. So how do we fix this? Well, there's a very simple fix. We just use a little bit more notation. So this, I haven't finished. This is partial w partial x holding y and z fixed. This is partial w partial y holding x and z fixed. See, problem solved. This is partial w partial z holding x and y fixed. In contrast, down here, this guy is partial z partial x holding w and y fixed. You see, I just have to fess up to what else I'm holding constant while I'm taking these partial derivatives. This is partial z partial w holding x and y fixed. This is partial z partial y holding w and x fixed. All right? So that's the notation which fixes it. Just use a notation which explicitly indicates what set of variables you're taking is independent, and then you've removed the ambiguity, and we can differentiate without trouble. All right? How about this? What if we have x squared plus y squared plus z squared equals to 1? And I want to find the partial derivative of z with respect to x. How should I do it? Here's how I do it. Very simple. I take the total differential of the equation. It gives me 2x dx plus 2y dy plus 2z dz. Then you know what I do? Simple as this. Solve for dz. So what is dz equal to? Minus x over z dx minus y over z dy. So this is that method of differentials I was talking about. We take the total differential of the data that we're given, and then we interpret. So here my interpretation is I'm taking z to be the dependent variable. That means I solve for it. What's left over are the independent variables, differentials, in this case x and y. The coefficients are the partial derivatives. So this expression tells me that partial z, partial x is minus x over z. And it also tells me that partial z, partial y, is minus y over z. We get 2 for the price of 1. Yes, sir?
Where did you get the 2x dx plus 2y dy and that first thing that you wrote?
Indeed. Where did that come from? And this was equal to 0. Sorry about that. Taking total differential. So if you want me to put into words what the total differential is, to take the total differential of an expression, pretend all of the variables are independent. And you're just differentiating them, assuming no relation between them, except for the one which is given, namely that algebraic condition. That's how we take the total differential. Is there another way to do this? Here's the way I might commonly teach Calculus 3 to do. I mean, this is a good way. I think you guys can understand this. But here's an alternate route if this leaves you unhappy, my current way of thinking. Alternate route. For those of you who wish to live life more mundane, how about this? We have x squared plus y squared plus z squared equals to 1. We're assuming what? We're going to assume that z is a function of x and y. And then we're going to take x and y independent. What's that mean? X and y independent. In particular, that means like partial y, partial x is 0, and partial x, partial y is 0, right? So simply take the equation which you're given and differentiate it with respect to x. What happens? What happens when I partial differentiate that with respect to x? I get partial x of x squared, right? Plus partial x of y squared plus partial x of z squared equals to partial x of 1. I'm using the additivity of the partial derivative, right? That the partial derivative of a sum is the sum of the partial derivatives. This is in fact true. Now, one of these things, it doesn't matter how sleepy I am, I can calculate this piece. It's a 0, right? Well, actually, that's not obvious that that's 0 unless you have clear in your mind that x and y are independent variables in this question, right? You might say my question was not clear because I didn't say x and y were independent variables, right? I just said calculate partial z, partial x. What's the defense of my sloth? The defense is, well, what else could the other independent variable be? If I'm using z as dependent and x as independent, what are my choices for the other independent variable? Like, this has to mean partial z, partial x, holding y fixed, right? I mean, that's not debatable. Which is the excuse calculus books use for not introducing this notation to you, many of them. Thomas's Calculus is a very good book. Not all calculus books discuss partial differentiation with respect to side conditions, which is a sad, sad chapter in calculus book writing history, because thermodynamics is almost all about this kind of partial differentiation. How many of you have to take thermodynamics? A lot of you. You will face this calculus. It is going to be real. All right? So you need to like sort through some of these ideas. They're not hard if you understand what's going on. So that's why I'm trying to give you tools so you can, when you get to that, understand it. But and actually, I have about a half a dozen thermodynamics examples in this section for that reason. Ideal gas law and other things. Okay, enough jibber jabber. 0, what's this? 2x, right? This, now that's where you have to be careful. Z is a function of x and y. Chain rule applies, right? So that's plus 2z partial z partial x, right? So therefore, solve for partial z partial x equals to minus x over z. What do you know? We found the same answer. Now, the second way I just showed you to do it is certainly less adventurous, right? This is kind of a natural extension of what you've already been doing, right? If I was teaching a dumber crowd, I would just give you the second method and let you suffer in your ignorance. But you guys are smarter, so I have showed you the secret path, which is the method of differentials. Take the total differential of the expression, you can extract all the partial derivatives that your heart desires from one silly little calculation. Check it out. If I wanted to find partial derivatives of y with respect to x and z, how would I do it? Yeah, solve for dy. Yep, that's it. dy is minus x over y dx minus z over y dy. And so like partial y, partial x, holding z fixed, is minus x over y, and partial y. Oh, oopsie. That was a z. So sorry. Oh, I'm sorry. That was sad even for me. Let's see here. Partial y, partial z, holding x fixed. Yeah, minus c over y. So there you go. 2 more partial derivatives. And so it goes. Let me show you a standard. I mean, everybody gets to see this example when we get to this part of the course. So I should show it to you guys. So Roger Penrose, in his book Road to Reality, this is one of his. I guess he has a friend who says this is one of the fundamental confusions of calculus. I've already showed you one of those, which was the partial differentiation versus total differentiation of x we saw last time. That's one of them, if I remember right. But this is the other one. So if I ask you guys, if we do, say, partial z, partial x times partial x, partial y, times partial y, partial z, that should be equal to what? Like the y's cancel? Yeah, it should be 1, right? Here, we're assuming that f x, y, z is equal to 0 for some nice function, differentiable function, right? So is it 1? Let's work it out. If we have some function, so this, for example, we've worked a specific one of these already. This last example was such a thing. This is the quote-unquote f of x, y, z, right? That's the form of my first example. So, well, anyway, so if we have f of x, y, z equal to 0, take the total differential of this, what's it look like? It's fx dx plus fy dy plus fz dz. So you can solve this thing, right? We can solve this thing for dx, you can solve it for dy, you can solve it for dz. Dx, I get minus fy over fx dy minus fz over fx dz. For dy, I get minus fx over fy dx minus fz over fy dz. And finally, solving for dz gives me minus fx over fz dx minus fy over fz dy.